All right, so an antiderivative is the exact opposite of a derivative. So we're working backwards. And that's really the moral of the story there. And a basic example is that x squared is an antiderivative of 2x, because if I were to take the derivative of x squared, it becomes 2x. Okay, so what a question would be asking you would be something along the lines of, what is the antiderivative of 2x? All right, so you can make a little note of that. All right, so your answer would be x squared. Now, it's not as simple as that, as you can see further on. You see there's a little plus c action going on there. So what I would say is that it's x squared, or at least for the 2x, but plus some constant that we call c. All right, because you have infinitely many antiderivatives of a function. If I took the derivative of x squared plus 1, I would get 2x. If I took the derivative of x squared plus 7, I would get 2x. X squared minus 13, I would get 2x. So it doesn't matter what the constant is. Whenever I take its derivative, I'm going to get the same result, that same 2x. So we always say plus some constant c. All right? And so that's how we distinguish the fact that it could be any possible numerical value added onto the x squared, making the antiderivative. All right? This next part is where we connect to the last unit when we talked about differentials, because we're going to create something called a differential equation. All right? And so if you follow the progression here, we have y equals x squared plus c, which is what we came up with over here. Its derivative, if we were 2 units ago, and I just said find the derivative of this, you'd say dy dx equals 2x. But in the last unit, we knew that if we just multiply both sides by a dx, we would get it into differential form. All right. So that transition is what's going to allow us to set up an antiderivative. All right. It's called integral notation. All right. So the weird part, maybe unnecessarily weird part, is that antiderivative and integral, they're synonymous. So they mean the same thing, all right? At least in the early goings. We'll come up with some differing definitions for the two terms, because it's really what you use them for that'll kind of dictate when you would call something an antiderivative versus when you would call something an integral, all right? So, but essentially we're really talking about the same thing, all right? So we introduced this funky new notation, that weird little S-looking thing. That is the integral symbol. All right. What it's telling us, if we're just looking at this guy right here, I'm always the funky S and the dx is telling us take the antiderivative of the thing contained between the funky S and the dx. All right. All right, so it's just really a command. It's saying, find an antiderivative of this. Now, you'd be given a specific function, and so if I said specifically find the antiderivative of cosine of x, you would be thinking of the function that has a derivative equal to cosine x, which would be what? What function, when I take its derivative, gives me a cosine x as a result?
Sine.
Sine x. So we would have sine of x plus c as our answer. All right. So you notice how the lowercase f becomes a capital F. We use a capital F to represent an antiderivative. All right. So that capital F is the notation that we would use for an antiderivative. So just kind of off on the side here, a little bit more with the notation. We kind of look at f of x as our benchmark. That's where we start. You could do a few different things from there. One thing you could do would be to take a derivative, f prime of x. Maybe a second derivative. But starting with that benchmark, f of x, you could also go backwards and take an antiderivative, which we would call capital F of x. You could take the antiderivative of an antiderivative, but that you don't really get into the notation for that sort of thing because there's some information that you need to flesh out before you can go from one antiderivative to another. Right? And that's basically this plus c. Sometimes we could figure out what that c value is, sometimes we can't. Right? So our answer may contain a c in it in some circumstances, and it may not in others. Right? So it's a little bit of the notation, and you'll get more familiar with it as we go. And all of this has been pretty much addressed. I mean, we have a name for the f of x. We call it an integrand. So like under a radical, we call it a radicand. So, radical becomes radicand when you put it under the radical symbol. Right? An integral it becomes an integrand when you're focusing on a particular function. All right, so just a little bit of wording there. The variable within integration, right, that should make sense. It's the variable within the function. C is the constant of integration, and all that means is the constant that you gain through the process of taking the antiderivative or integrating. All right, and so these are our basic rules. It's really the only set of things that you would need to commit to memory. I mean, there's some other things that maybe you would want to commit to memory, but these are the ones that you would have to. You really can't do anything without this information. But fortunately, it's all based on your knowledge of derivatives. All right. So again, it's really just asking you, if I'm looking at the 0, which is my integrand, what would I have originally as a function that if I took its derivative would give me a 0 as a result? I think I heard it.
Yeah, no,
C. Yeah, some constant C. Poor quality C. Yeah, fix that. Not much better. Let me bring it in a little bit. Third time. Okay, I'm just going to settle with that. All right, so it could have been anything. It could have been a 5 as a derivative of 0. Could have been pi, could have been e. Any constant would have got the job done. Could have been a fraction, decimal, any other kind of irrational number. Some constant. That's the magic idea there. Now k, all right, so this is where it gets a little weird because not all constants are created equally. So this k here is also a constant, but not of integration, right? So it's a constant particular to a function. All right, so you might think back to like Algebra 2 pre-calc. There were some formulas that you learned, especially with exponential growth, for example. You would have a formula like n equals n sub 0 e to the kt power. You don't really need to know the formula, just the fact that there was a k in there, and that k represented a rate of change. Right? And you have to be given that rate of change in the problem. Right? That's really what we're talking about here. You're given some constant particular to a situation. Right? A gravitational constant, for example. All right, a constant related to boiling points for different liquids. Just something that's known basically either in a science or business sort of application, but the key word there being application, right? So it's a known quantity. We just don't happen to know it right now, all right? So let's pretend I did know it. Let's say it was the antiderivative of 2. What would the antiderivative of 2 be? 2x. Okay, what if it was 5? 5x. All right, what if it's k?
Capital.
Kx.
Capital.
Well, we're going to keep it as a lowercase.
Okay. I thought I was right. I was wrong.
And you know what? I've learned in life that you can go in the wrong direction as long as you do it boldly. That's why no matter where I am, foreign country, local, different state, doesn't matter. somebody will always stop me and ask me for directions. I could have just got off the plane.
You look confident.
I always look like I know where I'm going. I have no idea though.
So you convince anyone of anything as long as you just say it confidently.
That's why there's so many people in this world that have jobs that they're not qualified for. They interview well. Like, yeah, we'll look past the fact that you have zero qualification for this job. We're going to give it to you anyway because you have talked to us the right way. All right, so kx plus c. All right, this is a constant. The constant's not going to change. All right, so if it were 3, it would be 3x. If it were 10, it would be 10x. All right, so k becomes kx. All right, the next one is k multiplied by a function of x. All right, that's a different story because there's not really much we can do here without knowing what the function is. So our answer is going to be notation heavy. But just like there was a constant multiple rule for derivatives and limits and just about everything, there's a constant multiple rule for antiderivatives. So I can pull the k out and get k times f of x dx, all right, as an integral. All right, k is going to work my way into my antiderivative. What is the antiderivative of lowercase f of x? Capital. That's where the capital comes into play. So capital f of x, but always a plus c on at the end. All right, so any kind of assessment, whether it's a quiz, individual quizzes, there's still a possibility, you know, not like full period jammies, but like exit tickets, things along those lines. Group assessments, any other kind of assessment, projects. When you take an antiderivative, if you don't have the plus c there, it's not right. All right, so you'd be incorrect, and therefore I'd have to take off credit every single time you make that mistake. All right, so because that would mean, like, if I gave you 10 questions and you missed a plus c, every single one of those questions are wrong, so you lose credit on every single one of them. That's how important the plus c is. All right, so you gotta train yourself. All right. Now the next one, again, notation-wise, it looks pretty funky, but it's a power function. Power functions are easy enough to handle because for derivatives anyway, we have a power rule, right? So we would take the power and multiply by the coefficient and then reduce the power by 1. That's if we were taking the derivative. But we want to take the antiderivative. So I want to do everything backwards. All right? So originally, again, I'll just write it down. Multiply. So this is for derivatives. Multiply power by coefficient. Reduce the power by 1. All right, let's do the exact opposite of that. So instead of working down the list top to bottom, let's work bottom to top. And do everything the exact opposite of this process. So instead of reducing the power by 1, I would do what?
Add 1.
Add 1. Instead of multiplying the power by the coefficient, what would I do?
Subtract or divide it.
Divide. All right, so divide the power into the coefficient. Is that my final answer, you think?
Plus c.
Plus c, yeah. You knew what I'm going for there. I mean, the x to the n plus 1 over n plus 1, that's hit or miss because that's new, but the plus c, you got to know that that's going to be there. All right, so you could test that out for a particular function, but you're going to have plenty of opportunities to do that. All right, so make the n value a 2, for example. So x to the third over 3, or 1/3 x to the third. Take its derivative, and you'll see that it does play out. All right, but again, right now we're just inventing rules, so we'll actually apply them in a little while. Antiderivative of cosine is? Sine of x plus c. Antiderivative of sine x is? Negative cosine x plus c. All right. You only get that if you know your derivative rules. All right. So if all that seems like black magic, it's because you don't know your derivative rules. When people ask me, they say, "I'm struggling with antiderivatives. What can I do to prepare?" I'm not going to give you advice on anything specific to antiderivatives. I'm going to tell you to go back and learn your derivative rules, because those are the only things that would be keeping you from understanding this. Antiderivative of secant squared? Tangent plus c. All right, so we got a whole list of rules here, and a lot of them I don't know that you would need to memorize, because it's just what would give me a cosine if I took its derivative? Sine. What would give me a sine if I took its derivative? Negative cosine, and so on. All right. Antiderivative of cosecant squared. Negative cotangent. All right, and that's because cotangent has a derivative of negative cosecant squared, so we correct for it by negating. All right, antiderivative of secant x tan x.
Tan x secant.
It's going to be secant. Derivative of secant x is secant x tangent x. All right, antiderivative of cosecant x cotangent x. Close. Negative cosecant x. All right. 1 over x. What's that antiderivative going to be? Natural log of x. ln of x has a derivative of 1 over x. What about e to the x? E to the x. Good stuff. A to the x. All right, so for this one, and it does involve a log, but it would be the same idea. If I wanted the derivative of a to the x, I would first rewrite the a to the x. Multiply by the derivative of the exponent. Multiplied by the natural log of the base. The base here is a, so multiply by the natural log of a. So I'm going to divide. I'm going to do the exact opposite. Divide by the natural log of a. I'm going to divide by the derivative of the exponent. Well, derivative of the exponent is 1, so that's not going to factor into it. And then I'm also going to rewrite a. That's the one part where it's not like you can't quite do the exact opposite. What? Unrewrite it, like erase it. So a to the x over ln of a plus c. All right, and again, something you could test out. Just make up an a value, 2 to the x. Okay, 2 to the x would have an antiderivative of 2 to the x over ln of 2. All right. So basic rules, all based off of prior knowledge. So, but for whatever reason, you throw that funky s in front of us, an expression, and all of a sudden it's like, oh, what is this nonsense? I don't get it. It doesn't make any sense. But when you realize that, at least in the early goings, we'll talk about why these symbols mean what they mean, but in the early goings, all you need to know is that whatever is contained between the funky s and the dx is what you're finding the antiderivative of. That's it. That's all you need. So the problems on the next page, they're all just kind of putting this stuff into action. All right. Some of them you have to modify first. All right. So for example, in number 1, I don't like 1 over x to the 4th. I don't like it for derivatives, and I definitely don't like it for antiderivatives. Right? I'd rather write that as x to the negative 4th power. So it's the x to the negative 4th power that I have to find the antiderivative of. So the process there, again, it's the reverse of the power rule, aka the reverse power rule. Increase the exponent by 1, divide by the new exponent. right? So the exact opposite. And again, do you need a rule for that written down? No, you just kind of reason it out. So x to the negative third power over negative 3 plus c. Don't forget the plus c. You could also write that if you want. It's not necessary, but negative 1/3 x to the negative third plus c. You could even write it as negative 1 over 3x squared. Sorry, 3x cubed. That would be some math magic there. Negative 1 over 3x cubed plus c. They all mean the same thing. And just like when we were first learning about derivatives, with antiderivatives, we don't simplify unless we have a good reason to. All right? Number 2, that doesn't look like it fits any of the rules that we just came up with. So it's like, wow, what is this nonsense all of a sudden? But just like we had a sum and difference rule for derivatives, we have sum and difference rules for antiderivatives. Meaning, I can find the antiderivative of each part of this sum or difference and then put it all together later on. So what that would equate to, I'll write it out just this once because I find it's more trouble to actually write it out than it is to actually do it. So this would be the same as saying 3 to the x dx as its own integral minus e to the x dx as its own integral minus x cubed dx as its own integral plus x to the e dx as its own integral. All right, once you realize that you're just taking the antiderivative of each part and putting it all together, you skip this step. All right? So at least in the early goings, especially when you come up against something like 3 to the x, that's the one I find that people forget most often. That would be the a to the x. So we would have 3 to the x over ln3 minus e to the x, indeed, plus, now it's got an e in it, so it's obviously a trick question. It's not exponential. X to a numerical power it's a power function. So we're going to apply the reverse power rule there. So x to the e plus 1, oh, that's not an x. E plus 1 or 1 plus e either way, over e plus 1 plus c.
You don't need to put like C for all of them.
That was going to be my next point. So you can go one of two ways, but both ways will lead you to this final answer. You can assume a single constant added on at the end, or you can do a plus c for each one of these. All right. So what would happen if I had 4 plus c's and I put all those c's together? What kind of number would I get? It would still be a constant. All right. And since c represents any constant, it could also be the sum or product or powers of other constants. So if I had, for example, c times c, the answer would be c. C divided by c is equal to c. C to the cth power is c. C plus c, c plus 10, c plus 10c. They're all c. Everything's c. All right. The only time it's not c is when you throw in a variable. So if it's c plus x, it's c plus x. Right? Because c won't absorb a variable, but it will absorb all other constants. All right. They call another name for it is an absorbing constant. All right. So it'll incorporate every other constant into it. It's like the 80s horror movie, The Blob, if you've ever seen that. It's a terrible movie, but it's good if you like to laugh at terrible movies. Antiderivative of 5 cosine x?
5 sin x.
5 sin x plus c. An intermediate step might be to write it as 5 times the antiderivative of cosine x dx. But you can just intuit that part of the process. You don't actually have to write it out. All right, number 4 is the last one we'll do together. Then after that, you can try some other ones on your own, or at least I'll set you up on number 5. It's much easier than it looks at first glance. All right, but this one is the first time where they don't just say, here's an integral symbol and some stuff, do antiderivatives. It says, find the general solution to the differential equation. So this is where we have to first put it in differential form. So we'd be looking at dr equals pi d theta. All right. The integral, that concept, it's an operation. It's not as simple as addition, subtraction, multiplication, division, but it's still an operation. All right. So if I want to solve a differential equation, what I want is r's and thetas, not dr's and d thetas. Right? So the only way to make that happen would be to take the antiderivative. Right? But if I take the antiderivative of one side of an equation, I have to do it to the other side. All right? It's just like any other operation, like a radical, for example, or power. If you square one side, you have to square the other. All right? On the left-hand side, it seems like something's missing, but there's an implied 1 there. Because it always has to be funky s, a function, not always of x, obviously, because you don't see an x here, and then dr. If there's nothing there, it's not like it would be a 0, because the whole thing was 0 out. If you multiply anything by 0, you'd have a problem. Although, in this context, it really wouldn't 0 out, it would go to a constant. But you'd have to specifically see a 0 in there in order for the 0 to exist. If there's nothing there, there's an implied 1. All right. And the reality is, and this is something that we talked about briefly when we talked about differentials, this really is the product of something and dr. Just like this is the product of pi and d theta, because it gives us the area of the rectangle that would approximate the area under a curve. All right. So this is telling us a base and a height of a rectangle. If there's nothing there, then one of the dimensions has to be equal to 1. All right. That being said, what would be the antiderivative of 1? Normally x, but this time it's going to be an r, right? So r, and I'll write the plus c here just to show you. Just to show you how unnecessary it is to write the plus c. On the right-hand side, I would have what? Now this time it's pi theta. And I'm going to color code this properly, I guess. All right, so if our goal here is to solve a differential equation, or we're trying to solve for one variable in terms of the other. That's the thing, all right? So I could subtract c from both sides, but can we guarantee that those c's are equal to one another? No. So result would be plus c. All right? Now, if you think about it, I mean, if you really want to get philosophical, even if they were the same, constant minus a constant that were exactly the same, the result would be 0, which is what kind of number? Constant. That's actually the definition of something that's constant. All right? So a 0 could actually be written as some constant value. Now, if you happen to know that it is a constant value that is equal to 0, then of course you'd write 0. But because we cannot guarantee that those two c values are exactly the same, we can't assume 0. And in fact, if you really want to convince yourself, call this constant 1 and constant 2. We'd be subtracting constant 1 from both sides. All right? So what you'd actually get is a fresh new constant 3. All right? But nobody ever writes the subscripts because it's not necessary. like at the end of the day, if somebody were to say constant 17 is equal to 20, it's like, okay, cool, I didn't need to know that it was the 17th constant that you came up with. I just needed to know what the number was, so that would be the end of it. All right, so pi theta plus c. Does anybody know what kind of equation this is? It's a pre-calc concept late in the year. Also gap, it was something that was covered in gap too. Very briefly though in gap. It corresponds with a mode in your calculator.
Oh, polar?
Polar, yeah, is that what you're gonna say? Yeah, good stuff.
Sorry.
Yeah, polar equations. Right, so if you were to graph this without the plus c, you get something called a spiral of Archimedes. It's pretty cool. But it's also, actually let me just show you real quick. You don't have to do this, it's just one of those fun bits of math that you're surprised that it works the way it does.
So before you put the subscripts for C1, and we decided that we're subtracting C1, and then it's just like minus C on both sides, how do you decide that it's gonna be plus C on the right side of the equation? Like
You can go on either side, but if our goal is to solve for one variable in terms of the other, then it just was simpler to put it on the right hand side.
Okay.
If I put it on the other side, I'd have pi theta, in which case I'd have to divide out the pi. So less work.
Okay.
That's my justification for just about everything I do. So you put it into polar mode, your R equals replaces the Y equals that you would have in function mode. So every mode changes. We did parametrics before in this course, polar. So if I just did the pi theta, the xt theta np would bring that up. And I could just do a standard zoom, and you get that. And so what that's telling us is that the rate of change at any point along the curve, meaning if I were to draw a tangent line really anywhere along the curve of this spiral, its slope would be equal to, or at least in polar world, its quote unquote slope would be equal to pi, which is really interesting to think that would be the case. And then also to really think about it, it's like, well, how could that be the case? Because if I draw a horizontal line here, that would have a slope of 0. But these aren't x's and y's, these are r's and thetas, so your tangent relationship works differently. All right. So we'll explore that a little bit more later in the course, but just a little bit of a taste. I think it's pretty cool anyway. Now number 5, like I said, I'll just get you started on this one because it looks like something that doesn't even fit remotely with what we were doing. But if I tell you that you can just break up the fraction into 3 separate fractions, and then simplify each one so that it goes to power rule form, you'd be looking at x to the negative second, doable by power rule, plus 2x to the negative third, also doable by power rule, minus 3x to the negative fourth, same deal. Now I might as well just go the distance here. And we learned from number 2 that we don't actually have to write them as separate integrals as long as we know that we're taking the antiderivative of each part. Yeah, really, just because it's a question that eventually gets asked and addressed. The difference, again, between antiderivative and integral, it really means the same thing. But if you think of one as a noun and the other as a verb, that's probably a good way to go. The integral is the thing that you're presented with, telling you that you need to take an antiderivative. All right? The antiderivative is the action that you use to find the result of an integral. All right, so in that context, it's pretty clear that they're essentially really interchangeable terms. All right, so what's the antiderivative of x to the negative second?
X to the negative first divided by negative 1.
Right, so x to the negative first over negative 1. You could write that any way you want. I'll just write it the way you said it, which is good. How about 2x to the negative third?
2x to the negative second divided by negative
2x
2.
to the negative second divided by negative 2. And then the third one?
3x to the negative third divided by negative 3. Plus c.
And then your plus c. All right. Now, if you clean these up, it ends up being kind of nice. You get negative x to the negative first, minus x to the negative second, minus x to the negative third plus c. But you know at this point, we've been doing this long enough that you don't simplify unless you have a good reason to. And there's enough times where you have a good reason to that, you know, you'll get your practice. It doesn't need to be in every single case.